Good day, great of learners, and welcome to our Physical Sciences live broadcast. It's paper one today. My name is Temba Ngube. This session is proudly brought to you by Free State Department of Education in collaboration with Pagama Research and Development. Right, so today it's on the eve of our preparatory exam. We have come up to this far in as far as the physical sciences is concerned, and today we will take the next 90 minutes or so to try and remind ourselves of what is important insofar as our exam preparation is concerned. So we will try and cover as much ground as we possibly can, but also trying to pay careful attention to some of the most important aspects of the content that we've covered up to this far, without also undermining those that little detail that is very, very important. So because of time constraints, we will do so much for today, with the hope that this session serves to remind you of what is important, and in terms of our readiness, what are the things that we also need to remind ourselves of. Right. So without any waste of time, we remember very well that physical sciences is divided into two subjects. Okay, it's two subjects in a true sense, because we've got physics, which is paper one, and chemistry, which is paper two. So the combination of the two, then we refer to it as physical sciences, as you remember. Now, today we are focusing on the physics. Okay, now it's got 150 marks, which is the total, right? So the total is 150 marks, right? How is the 150 marks broken down? We've got section A, which is 20 marks, and section B, which is a long questions or structured questions, that is 130 marks. So that is done in a duration of 3 hours, right? So the 150 marks, we are not choosing, we answer all questions to the best of our abilities. So today we'll also take a turn to try and look at the techniques of responding to certain type of questions that we'll use as an example for the purpose of our revision, just to remind ourselves of what is important. So there will be your five or your four knowledge areas, which is mechanics. Okay, remember, mechanics is divided into Newton's laws, vertical projectile motion, linear momentum and impulse, work, energy, and power. Right. So there will be 4 questions in section B that are based on mechanics, which is Newton's laws, as we know them from grade 11, uh, vertical projectile motion, which we did this year in term 2, and then we've got linear momentum and impulse, which we did in the first term, and then we've got work, energy, and power, which we did in term 2. Right. So that's why these carries the greatest weight, which is 63 marks of the 150. Right. And then we've got sound, wave, and light. Sound and wave and light is based on the Doppler effect, right? Where we talked about the phenomenon of the apparent change, in the observed frequency due to relative motion of, the source and the sound observer, right? And then we've got the third knowledge area, which is electricity and magnetism, which is also comparatively high. It's the second of the 150 marks, 55 on electrostatics, which would be typically on question 7. It also around electric circuits, as well as electrodynamics, where we looked at the Faraday's law, the motors and generators, AC and DC, and we also looked at alternating current, right? And then last but not least, which will be your last question, is based on matter and materials. So on matter and materials, that's where we have the photoelectric effect. Okay, right. So this gives you a total of 150 marks in a period of 3 hours. So for every 50 marks, it's 1 hour. So if there is 150, which is 50 times 3, which gives us the 3 hours, right? And then moving along. Now, as you approach the exam, there are your quick wins, what we want to think of as our low-hanging fruits, or these are the easy marks that each and every one of us must be able to collect by all means, right? So the exam is structured in such a way that if you have the basics, you are able to get the minimum pass requirement. So these are your quick wins. These are your easy marks. What are these? These are definitions. Remember, definitions is either 2 out of 2 or 0 out of 2. Sometimes it's 1 mark. If you are asked to define a concept in words, you don't write the mathematical equation. You define it in words. Pay attention to the keywords. Use the keywords in the correct context. Then, if you read your definition, it must make the correct or carry the correct scientific sense, right? And then if it's 0 out of 2, it means you have skipped or missed the keywords. So refer to the examination guideline for that. Which examination guideline are we using? Physical Sciences 2021. Sometimes you may be given a concept, it can be described, and then you are asked to give a term that describes that concept. Then you'll be told, for example, I'll make an example, motion of an object under the influence of gravitational force only. And they say, write the correct term. The correct term is free fall. It's still a definition. Now you've been given the definition, you must identify the correct term. So it works both ways, right? Now, and for every long question in section B, this is structured questions, you'll be required to remember a definition or two. These are the easy marks. So go back to your exam guideline, remind yourself of those key definitions. For every question or concept, there'll be the obvious ones. If I can use electric circuits, for example, it's either you'll be asked to define EMF, you may be asked to define current, you may be asked to define potential difference or voltage, you may be asked to define EMF. So those are or state the Ohm's law. So these are the obvious. You need to anticipate what type of destinations may be asked, because there's quite a lot of repetition again around definitions. So, and definitions do not change because it's a concept on its own. It remains as such, right? Okay, and always refer to the data sheet. Okay, if you are carrying out routine calculation and then the question says 3 marks, okay, remember the 3 marks is for formula, substitution, and then correct answer with the correct what? Unit. If it's a vector, we must also include what? Direction. Okay, so the mark allocation also is an indication of what you need to do in presenting your solution. And there's a very important instruction that says show all your calculations. It means for every important step in your calculation, you need to show it clear so that the examiner can follow your scientific argument that you would have presented in your response to a particular question. All right. And then we've indicated that definitions are all or nothing. It's either you get the full marks or 0. Okay. And then another key thing, multiple choice, 20 marks. Okay. This is section A. Remember, the 20 marks, these questions are of different levels. Some are demanding, you need to do more to get the same 2 marks. So in terms of time allocation, you need to allow yourself enough time to answer the 20 marks. You cannot give yourself 5 minutes to answer 20 marks because now options are provided. Okay, so you don't leave multiple choice blank. We'll look at the technique of how you answer a multiple choice, which is something that we've been discussing all along, right? But we'll take time today just to remind each other of that. Okay, so we've spoken about the keywords and they must be used in the correct context. Very, very important. Right. The stuff that we did in grade 10 that will be called upon to recall or to remember or to apply, because senior certificate or what that which you refer to as matric is a 3-year course. We studied physical sciences in grade 10, went to grade 11. So grade 12 is not the matric, it is actually the exit of this 3-year course that we are doing now. Okay, now we are at the very end, it's the home stretch. Now in grade 10, we looked at the principle of quantization of charge. This is in electrostatics. Okay, this is in electrostatics. Okay, it shouldn't be gone with the wind. So when we talk about the principle of quantization of charge, we are saying Q is equals to NE. This is a very, very important equation that represents the principle of quantization of charge. And then you need to ask yourself, what exactly do we mean when we say charge is quantized, right? We're saying that every charge that's Q in the universe is an integer that's n, which is a whole number, multiple of the elementary charge. So the charge that exists on a material is in multiples of the charge of a single electron. That's what the law says. Okay? So you can remove a whole number of electrons from a material. Equally so, you may add a whole number of electrons. You can't add half an electron. So for charge to be quantized, it should be in multiples of the elementary charge. So n multiplied by E, n is the whole number, which is the integer, multiplied by the elementary charge, which is negative 1,6 times 10 exponent negative 19 coulombs. This is the elementary charge, which is a physical constant. So remember, in case you are stuck, go to your data sheet. Be able to distinguish between the mass of an electron and the charge of an electron. And then we spoke about the law or the principle of conservation of charge, where we said Q nu is equals to Q net over 2, right? So this has to do with the interaction of charges. So if two materials come into contact during that physical process, and this typical physical process occurs in what we refer to as an isolated system, we are saying that the net or the total charge remains constant before the physical process and after the physical process. Hence, the principle of quantization of charge says to us that the net charge of a closed system remains constant. Right. So we need to understand that as well. And then this is by far a very, very important concept in grade 10, where we dealt with motion in one dimension or linear motion, right? For us to understand vertical projectile motion, we need to first have a clear understanding of horizontal linear motion in terms of what we refer to as linear motion or motion in one dimension with respect to constant or uniform velocity and constant or uniform acceleration. So there's two types of motion that we've studied in these 3 years. We either have uniform velocity or constant acceleration. So the word constant and uniform, we will use them interchangeably to refer to the same thing. So when motion is constant, it is uniform. So when we are saying that an object experiences a constant velocity or a uniform velocity of, say, for argument's sake, 2 meters per second, what are we saying? We are saying that the position of the object changes by 2 meters every 1 second, which gives us the 2 meters per second, right? Okay, that's our constant velocity. And then when we talk about constant acceleration, A is equals to delta V over delta T. A is equals to, say for argument's sake, 5 meters per second divided by 1 second. Okay, excuse me. Now, we are saying if the constant acceleration is 5 meters per second squared, what does it mean? It means that the velocity of this object changes by 5 meters per second every 1 second. So the change in velocity can either be an increase or a decrease. If an object's velocity increases uniformly per unit time, that object is described to be having a uniform or a constant acceleration. So in other words, it's moving faster and faster. Another catch, if an object moves faster and faster going forward, it means the direction of motion is forward and the direction of acceleration is forward. So in other words, we're saying that the object accelerates in the direction of motion. That's a very, very important concept. Now, on the contrary, if we look at an object that slows down uniformly to stop, whether it end up stopping or not doesn't matter. But if an object is moving slower and slower, this object is moving forward. That's the direction of motion, is forward. However, if it's slowing down going forward, it is accelerating backwards. So the direction of acceleration is opposite to that of motion. So constant and uniform acceleration will actually differ in that way. So that negative acceleration suggests that the direction of acceleration is opposite to that of motion. So if the object was moving north, its acceleration is south in that order, right? So I genuinely feel that this is very, very important. And then we spoke about the principle of conservation of charge, where we said E Mac at position A is equals to E Mac at position B, right? So what are we talking about here? We're talking about the total mechanical energy of an isolated system being constant or remaining constant or being conserved. Okay. Now, mechanical energy exists in two forms in a closed system. It's the kinetic energy, the energy by virtue of the object being in a state of motion. The faster the object moves, the greater the kinetic energy, as well as gravitational potential energy. Take note, it's not potential energy, it's gravitational potential energy. So this is the energy that the object has due to its position relative to the surface of the Earth within a gravitational field. That's what exactly what it means. So also remember, this is in a closed system. There are no non-conservative forces. Okay, only conservative forces act on an object. That's why the mechanical energy is conserved. So the reason why mechanical energy of a closed system is conserved is because there is no non-conservative force acting on the object, or in other words, we're saying only conservative forces act on the object so that its mechanical energy is conserved. Okay, so we're trying to break it down and try to understand how it comes from grade 10 until the exit in grade 12. This is where we are, right? And also, we've made reference to the formula sheet. Very, very important. The formula sheet actually gives us an understanding of the concept represented mathematically, right? So the equations of motion, one more thing, don't memorize them. You will be provided. Yours is to copy them correctly and know which one to use and how, right? Very, very important. Okay. And then there's more stuff in grade 10 that we spoke about. We also dealt with EM radiation, which is the electromagnetic waves, where we spoke about the visible range of the electromagnetic spectrum, where we've got visible light, and then we've got Roy, G, B, I, V, right? So this is the visible range of the electromagnetic spectrum. So these are your 7 colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet, right? So if we were to write down the list in a particular order from low frequency to high frequency, then that gives us the whole range of different frequencies that we refer to as the electromagnetic spectrum. So we would have radio waves, right? Okay, radio waves. we'll have microwaves. Okay. So one more interesting thing, microwaves are a type of electromagnetic waves. A microwave oven is an appliance, it's not a wave. So we need to distinguish the two. So the oven becomes an appliance that utilizes microwaves as a form of radiation. Okay, and then we've got infrared. Okay, so after infrared, there's red. So the word infra says before red. So before red comes, after that it's red. Okay, and then violet, then we've got ultraviolet, right? And then X-rays, okay, and then we've got gamma rays. So this is the electromagnetic spectrum in ascending order of what you call frequency, energy, and penetrating ability. And then we dealt with stuff on series parallel circuit combinations in grade 10, which we also escalated to 11 and 12 in that order, right? And then in grade 11, we spent a lot of time on Newton's laws and its application. So Newton's laws are about forces. So the moment you understand Newton's laws, you are sorted in terms of the mechanics, because vertical projectile motion is about Newton's second law. Linear momentum and impulse is about Newton's first law, second law, and third law. Work, energy, and power is about first law, second law, and third law, right? We also have the law of universal gravitation. Remember, you must be able to distinguish between Fg is equals to constant G m1 m2 over d squared. Okay, and then Fe is equals to K Q1 Q2 over R squared. Right. So this is the universal gravitation. It speaks to the masses and the square of the distance between the centers. This is Coulomb's law. It speaks to the magnitude of the electrostatic force between any point charges in space. You need to be able to distinguish. The other one talks about charges, the other one talks about masses, right? And then here on universal gravitation, we speak about the distance between the centers, right? So you must also be able to distinguish between those two, right? I think even the data sheet does provide each of those two, right? Okay, and then multiple choice, section A, 20 marks. We've already alluded to the fact that when it comes to the multiple choice, you need to allocate a decent amount of time for you to be able to do it without, leaving some of the questions unanswered, right? That's the worst that can happen. Now, there's a technique that you have to follow. So this slide will actually speak to some of those. So it's enough time for multiple choice, 20 marks, a minimum of 25 minutes to 30 just to do the multiple choice. Read the question, highlight the keywords, check, eliminate, go back to the question. Once you've identified what you think is the correct option, go back and read the question and ask yourself, have I answered the question correctly? Right? Okay, so also do not focus on the option that you think is correct. For those options that you eliminate, you must provide a reason as to why you think they are incorrect. Very, very important. Okay, now you will eliminate two options which are distractors, right? So if you eliminate two of the four, you are left with two. So if you have eliminated correctly the two distractors, it means your chance of getting it correctly now is 50% instead of 25%. Okay? So you also better your chances of performing in multiple choice. Okay? Now, Also pay careful attention to the keywords or words or terms that are written in bold, uppercase, in capital letters. Okay. Upon completing multiple choice, go through the questions and check if you really answered the question correctly or not. Okay. Here is a practical example of a multiple choice question. The velocity time graph below represents motion of an object under the influence of gravitational force only. Okay, I'm going to underline that. Motion of an object under the influence of gravitational force. So if I were to draw the free body diagram of this object, here it is. Fg is the only force, right? Now, what type of motion is this object experiencing? It is experiencing what? Free fall, right? So free fall is the type of motion, okay? Now, this object starts with a velocity of what? Of v, right? And v is not zero. It means not only is this object in free fall, but it is also a projectile, okay? It is a projectile. So what is a projectile? A projectile is an object that is given an initial velocity and moves under the influence of gravitational force only, right? So it is undergoing free fall. Why? Because it experiences motion under the influence of the gravitational force, right? Now, you are told that with the displacement of the object at time 3t is, we need the displacement of the object at time 3t, right? So now this object took, to go up, it took what? T seconds to reach the highest position from the point of launch. It took T seconds, okay? Reached the highest position, went back down faster and faster. And how long did it take to go from the highest position to the ground if it ended on the ground? It took double the time. So if you say T plus 2T, what do you get? 3T, which is exactly that. Okay? Now, this is a trajectory that we've drawn to show the motion of the ball. Okay? Now, the displacement, if the examiner says determine the displacement or distance using the graph, okay? Using the graph, you must calculate the area. So area of the graph for time t, area of the graph for change of position, which is displacement, is equals to half base times height. So this is the area that we're talking about for the upward motion. Okay, so it started at A, it went to B, it came to C, and then it went to D, right? So for motion from A to B, what is the displacement? The displacement is upwards, which is equals to half T multiplied by V. So it's half TV, if there's anything like that. Okay, and then for motion from B to C, change of position is downwards, right? Is equals to half 3t, right? Multiplied by negative 2v. There we go. Okay? So if you cancel that, you get what? Delta x for downward motion is negative 3 TV. So now the total displacement of the ball is half TV less 3 TV. So we can collect like terms there. Half minus 3 is 2.5. 2.5 is negative 3 over 2 VT, which is TV. Okay. Now you see, we have used the graph to get that. So the correct option therefore is what? Is C. Okay. Now it's important for us to understand that multiple choice questions are not necessarily of the same level of demand. Some may be straightforward, they might require you to remember a thing or two about a definition or a concept? Are you able to apply it? In some cases, you really have to apply your mind. And if you take this particular example, it wasn't your typical straightforward question. You needed to apply yourself and your mind to it before you arrive at the correct option. Okay, but for you to arrive at the correct option, you actually need to understand the steps that one must take. Okay, right. Here is another multiple choice. Okay, an object moving at constant velocity. One of the most important things is to underline the keywords. Okay, what do we know about motion of an object in which the object is experiencing a constant velocity? Okay, what's the science behind constant velocity? We know that for that object, if the object is moving at constant velocity, this is about Newton first law. Okay, the net force acting on an object is equals to 0 newtons. So if an object experiences a 0 Newton force, it's either the object is at rest or it moves at what? At constant velocity. Right. So wherever we see constant velocity, we must think about the science behind that in terms of the object experiencing a zero net force according to the Newton first law. Right. So the net work done, okay, if the net force acting on the object is zero, then they're saying the net work done on the object during the motion over a rough surface, right? So the object is moving at a constant speed. We know that work net is equals to work done by F net, right? And then work done by F net is F net, okay, delta X cos theta. So if F net is 0 newtons by whatever multiplied whatever change of position cosine of theta, irrespective, because if this is 0, then work net will also be 0 joules. Okay, right. So the net work is total work done by the total force. So work is done by a constant force acting on the object over that period or that displacement where there is a change of position from initial position to final position. So that gives us 0. So this question is actually more straightforward than the previous one, as we have seen. Here we needed to do some calculations here and there, apply our mind and our understanding, whereas in the next question, you needed to unpack the implications scientifically of what it means when an object experiences a constant velocity. Right. And then the Newton's laws are very, very important in terms of the 63 marks that are for question 2, 3, 4, and 5 in paper 1, which is the entire mechanics. It's about the forces. And the Newton's laws, they talk about the effects of a force. One of the most important ideas that we learned before we even reach grade 10, we know that what the effects of a force, what can a force do to an object? It can change the state of motion of an object. So we have already alluded that Newton's first law, this is N1, okay, it's not the highway, there is a zero net force and the object will either be at rest or it will move at what? Constant velocity, right? And then Newton's second law, the net force is no longer zero. So there is a non-zero net force. Okay, so the net force is not zero. So what's the consequence or the result of a non-zero net force acting on the object? According to Newton's second law, the object experiences a constant acceleration, right? And the acceleration is in the direction of the force. Now, in grade 10, we looked at what is constant or uniform acceleration. It means if there is a non-zero net force acting on the object's velocity will change by the same amount every second as the result of that non-zero net force acting on it. So it's either a non-zero net force acts on an object and the object moves faster and faster, or a non-zero net force will act on the object and the object will move slower and slower. Now, the similarities between these non-zero net force and acceleration is that they are in the same direction. So Newton's second law therefore says to us that a non-zero net force causes the object to accelerate in the direction of the net force. That's where it comes from. Okay? And then we've got Newton's third law, which talks about two bodies. Force by A on B is equals to force by B on A in the opposite direction, right? So if body A exerts a force on body B, simultaneously, body B exerts a force of the same magnitude on body A in the opposite direction. So the minus suggests that these forces are in the opposite direction. And these two forces, they are equal in magnitude. It's very, very important to qualify. What is equal about these forces is their magnitude. So these two vectors are not equal because the direction is opposite. What is equal is the size of the forces that these two bodies exert on each other. That's very, very important. So this talks about two bodies, right? And then let's see a practical example where we talk about Newton's laws and their application. We've got a 10 kg block that is connected to another block of mass M by a light inextensible string. I'm going to underline that, light inextensible. So this connecting string that I'm going to highlight, its mass is not going to be considered, and there's a constant tension force in the string as a result of the two bodies connected together by means of that string. So the string does not stretch and its mass will be ignored. The only masses that we're going to take into account in this system is the 10 kg and the mass M, which is unknown. Okay, now the blocks are placed on a raft. Okay, what does that raft tell us? It tells us that there is kinetic frictional force, okay, which we calculate using mu k multiplied by the normal force. Okay, so these two blocks experience a kinetic frictional force. Okay, there is a force of 45 newtons that is applied at an angle of 30 degrees to the horizontal, as shown in the sketch. The blocks accelerate. Oh, that's very, very important. Now, the moment we see the term accelerate, it means the blocks are not at rest. Number two, the blocks are not moving at a constant velocity. In actual fact, the blocks are moving faster and faster in the direction of the net force, as suggested by Newton's second law. Right? Now, we're told that block M experiences a constant frictional force of 1 Newton while it's moving. It's given. Now, this is of importance to me. Wherever there is an application of Newton's laws, because it's about forces, if we correctly identify the forces in the free body diagram, that's another source of our free or easy marks, right? Now, it says 5. Draw all the forces acting on the 10 kg. So this is a diagram that's free of the body. It's a free body diagram, that's what it means. So instead of drawing the 10 kg block, would represent the dot will represent the body, because it's a free body diagram. So it's a diagram that's free of the body. We don't represent the actual object. Instead, we represent it using a dot, right? So if it's 5 marks like this is definitely tells us that we are supposed to actually identify 5 forces, okay? In no particular order. There is this force that's pulling the 10 kg, this 45 newtons. Some of you call it the applied force. It's fine, I will write the applied force. Even if you say it's 45 newtons force, okay? Because that's what it is, okay? We've got the force exerted by the center of the earth on the 10 kg block towards the center of the earth, which is the force of gravity. Now, because the 10 kg block is on the surface, there is a normal force acting on the 10 kg block exerted by surface on 10 kg perpendicular to the surface. So if they accelerate to the left, it means the kinetic frictional force is to the right. because this is the force exerted by the surface on the block in the opposite direction of motion, right? Okay, so we are at 4 now. We need the other one. Yes, there is a string there which which gives a tension force that connects the 10 kg to the block of mass m. So let's count the number of forces that we have. It's the normal, the kinetic frictional force, the tension, the force of gravity, the applied force of the 45 Newton force. This gives us the 5 that we see there. So the Mach allocation for a free body diagram is an indication of the forces that must be included. Okay, very, very important. And this is actually easy marks that each and every one of us must be able to accumulate. And then we spoke about the keywords. The action word here is define. So when you define, you either get 2 or nothing. Okay? So if we define a normal force, what is a normal force? Okay? A normal force is a force exerted by the surface, okay, on an object it acts perpendicular to the surface. I'm not saying upwards, I'm saying perpendicular. So the exam guide will also give direction on these keywords, right? So for an object that is, let's say, hanging there like that, then there is the surface. This object does not experience a normal force because it's not in contact with the surface. So in other words, what we are saying is that the normal force is actually a contact force applied by the surface on an object. Okay, so if I were to draw the free body diagram of this one, I will have the weight, Fg downwards, and then let's say it's hanging there at rest, and then I will have the tension force done. There is no normal force. So let's not include the normal force if the object is not on its surface. Okay? Okay. Going backwards, it says here, calculate the magnitude of the normal force acting on the block, 10 kg block. We want the normal force acting on the 10 kg block. All right? So how do we get the normal force? Let's agree. We understand that according to this free body diagram, there is the object. Okay, there is the weight of the 10 kg block, mg, which is equals to 10 multiplied by 9,8, which is equals to 98 newtons. Right? And then we've got the normal force, there it is. And then we also have the vertical component of the 45 Newton force. Let's call it Fy. All right? Now, this object moves horizontally. It means if you add the normal force plus Fy plus Fg, you must get 0. And the sum of all these forces is the net force. This is the net force. Is equals to 0 newtons. Right? Now, we want the normal force. The normal force, okay, if we say upward is positive, the normal force, we don't know, plus, okay, if we have that force there, okay, and then we have got the vertical there, and then the horizontal there. So if this is 45, okay, if we go back to the diagram, this is the angle there, okay. So this is the horizontal component of 45, which is Fx. That's the vertical component of Fy of 45, which is Fy. So for us to get Fy, we know that sine 30 degrees is equals to opposite, which is Fy divided by 45. So Fy is equals to 45 sine 30 degrees. Okay, so if we can go back here, we'll have 45 sine 30 degrees. right? Is minus FG is 98, okay, is equals to 0. So if N and Fy are positive, then Fg is negative because they are in the opposite direction, right? So N, which is the normal force, is equals to, you transpose the 98, it becomes positive, less 45 sine 30, okay? 45 sine 30 on your calculator, what does it give you? It gives you 22.5, which is 22.5. Therefore, the normal force acting on the 10 kg is going to be 98 minus 22.5. Okay, this gives us 75.5 newtons. Right. I want to realize something. If we go back to this question is 4 marks. Now, where does the 4 marks come from? First of all, for summing up all the vertical forces to 0, that gives us a mark, which is the same thing as saying F net is equals to 0. And then substituting Fy, it's a mark, okay? And then what else? If you substitute the mg correctly, which is the 98, is another mark. And then for the final answer of the normal force, which is positive, because we took positive as upwards as positive, then that gives you the 4 marks that you are actually allocated there. Right. So in applications of Newton's laws, identify the forces correctly. This is in the free body diagram. You must also distinguish between a free body diagram and a force diagram. Very, very important. And then we have also highlighted or underlined the keywords rough, smooth, in terms of the availability of the kinetic frictional force or static frictional force. Okay, so we must also pay attention to the mark allocation. So if it's 3 marks, it's simple formula, substitution, and answer, right? Formula, substitution, and answer. That gives you the 3 marks, right? Also pay attention to direction, as we did in this case. Fg is negative, normal, and Fy are positive because they are in the opposite direction. Okay, and then if it's more than 4 marks, it says to us it's a multi-step type of a question. Right. Having said that, we'll just take a short breather for 5 minutes, and then when we come back, we'll take it from where we left. We'll still be discussing some of the tips and the strategies in terms of problem solving. See you after the break. Welcome back, grade 12. We're still on our live broadcast. Physical Sciences, paper 1, the last push for our exam. Towards the prep exam, we're still discussing mechanics and application of Newton's laws. Very, very important. And then there is the data sheet there for your use. Please be reminded again that it's important to copy the equations or the formulae as they are given in the data sheet without any effort or attempt to manipulate or change the subject, because that doesn't carry marks. And in a true sense, it's actually time wasting. So we must also try to effectively manage our 3 hours, right? Okay, and then we've got vertical projectile motion, which is most likely going to be your question 3, if that's the case. And then we've got the key terms there. We've defined free fall, which is a type of motion. Okay, the exam guide, I think, will guide you on that. Type of motion in which the only force, in which the force acting on the object is the force of gravity only. Okay. So the word only is very important, because we have seen that's our free body diagram of an object that is free fall. And then a projectile is an object. Okay. So it's very important for us to distinguish. The other one is an object, the other one is a type of motion. So it's an object that is given an initial velocity. Okay. Initially it's launched, okay, and then moves under the influence of gravity and influence of gravitational force. Of the force of gravity, right? Only. Very important. So in this case, because an object experiences the force of gravity only, it's a non-zero net force. That's why the object accelerates uniformly. So the acceleration is the change in velocity per unit time, or the rate of change of velocity, meaning the velocity changes by 9.8 meters per second every 1 second. In which direction? Downwards. Why is the direction of acceleration downwards? Because the net force is also downwards. According to Newton's second law, if a net force acts on an object, the object accelerates in the direction of the net force. Now that Fg is the only force acting on the object, it becomes the net force. And in which direction does it act? Downwards, which explains why the acceleration due to gravity is also downwards. Right. Okay. So if you see the term air friction is ignored, it means that the only force acting on the object is the force of gravity. Then this object is in what? Is in free fall. Very, very important. So Fg acts vertically downwards, then the object will accelerate in the direction of what? Fg. That's why there is a constant acceleration. So G is equals to 9.8 meters per second squared downwards. Suggests that the net force is downwards, which is why the acceleration due to gravity is also downwards. I think we've spoken about the equations of motion as we would recall them from grade 10. Right. And then what are the important steps that one must consider when dealing with vertical projectile motion problems? Number one, you must read the problem statement before you attempt. Seek first to understand. And then draw a trajectory. If an object is launched, let's say from the top of a building, it goes up and down. Draw something like this, which is we call a trajectory. So that's position A, that's position B, that's position C, and then on before hitting the ground is position D. That's what we mean when we talk of a trajectory. So that you can clearly have clearly defined points during the motion of the object, so that we consider motion between the initial position and the final position, because direction is also important, right? Because here we're dealing with what? Vectors, right? So the plus and the minus are an indication of direction. So if we say upwards is positive, it means downwards is negative. So the minus 15 meters per second velocity suggests that the object is moving downwards. That's the velocity of the object in its downward motion at a particular point or in time, or at a particular point in that trajectory, right? And then always refer to the formula sheet, right? Let's look at a practical example of vertical projectile motion. Okay, a small stone is projected. So this stone is launched. Okay, so the moment it says projected or launched, it implies that it is a what? It is a projectile, right? It is a projectile, right? With a speed of 20 meters per second. So the initial velocity is 20 meters per second upwards. That's why this object is indeed a projectile. Okay, and then it passes the roof of an 8-meter tall building, and then as it passes the roof, at point B is shown in the diagram. Ignore effects of air friction. What is this? This tells us that this is free fall. The object is in what? Free fall. Okay. Now write down the acceleration of the stone at point A. Write down. It doesn't say calculate. Okay, so it's either you know or you don't. Now, understanding that it's free fall, and we said that for any free falling object, the object experiences a what? A constant acceleration. Here is the acceleration. So at any point in that motion, the object experiences a constant acceleration. Of acceleration is 9,8 meters per second squared downwards. So 9,8 meters per second squared is the magnitude. Downwards is the direction. That's why we've got 2 marks like that. Okay? It doesn't say calculate. Now, it says using equations of motion, calculate. That's the action word. The time it takes the stone to reach point A. So point A is essentially the highest position, right? Now, what is important is this is our trajectory. Okay, there is the stone goes up and then down, right? So this is position B, that's position A, and then fine. It's launched from the ground. Yes, it's launched from the ground. So it's gonna be the other way around. Okay, it goes like that. Okay, so it's launched this way. So the initial, if we take upwards as what? Positive. Take upward, that's direction now. Is positive. Okay, so if we go back, we've got A is the highest position, B is the edge of the roof, right? So this is A, and then that's B, right? And that's 8 meters. Okay, so what are we saying here? We are saying that this ball is launched from the ground. We want the time that it takes to reach position A, right? Position A, which is the highest point, and that is 3 marks. So that we will consider motion from the ground until the highest position A. So we've got initial velocity is upwards, it's going to be 20 meters per second. Okay. What do we know? We know that the acceleration of the ball is downwards. So downwards suggests that it's negative 9,8 meters per second squared. Now, as the stone is moving upwards, it is slowing down. It's accelerating in the direction of the net force, which is Fg. That's why the direction of motion is opposite to that of acceleration. So the ball or the stone accelerates in the opposite direction of motion. Okay, we're interested in the time. We know at the highest position at A, it will stop. Okay, it's 0 meters per second. We're interested in the time that it takes. Okay, so we considered motion from here, the ground, until the highest position. Okay, so that change of position is upwards. Now it means Vf is equals to Vi plus A delta T. Okay, final is 0. Initial is positive 20 minus 9,8 delta T. Right? So we get a delta T of 9,8, 20 divided by 9,8. 20 divided by 9,8 from a calculator, it will give you 2,04 seconds. 2,04 seconds. Right. So 1 mark for the formula, 1 mark for the correct substitution, and then 1 mark for the correct answer, including the correct SI unit of time. Right? I hope it makes sense. And then calculate the magnitude of the velocity of the stone the instant it reaches point B. It's also 3 marks. Okay? It's going to be formula, substitution, answer. Okay? From the initial position to position B. So we'll consider the motion from the ground until position B. The change of position is actually upwards 8 meters, right? Because it starts here and ends there. So the direction is upwards. So change of position is 8 meters. We still have the same initial velocity, okay? We want to know how fast is it moving? And now we are able to say, okay, we don't have the time from the ground to B. So if we use Vf squared is equals to Vi squared plus 2A delta Y. Okay, that's the equation. This is the velocity final when it reaches point B. We don't know. That's what we are looking for. Okay, initially it's 20 squared plus 2 negative 9,8. What's the change of position? It's upwards, it's positive 8, right? So Vf squared is equals to, so if we simplify that, 20 squared, okay, minus 2 times 9,8 times 8. Okay, what do we get there? 243,2. 243,2, right? But we're looking for Vf, so we find the square root of that. Okay, but remember, when it reaches B, it's moving downwards. So that velocity must be negative. So it's going to be plus, minus, or minus the square root of 243.2. Square root, okay, we get 15,59. 15,59 meters per second downwards. Because when it reaches point B, it's moving in which direction? Downwards. So 1 mark for the formula, 1 mark for the substitution, 1 mark for the answer. This gives us the 3 marks that are actually located. Right. Okay. And then linear momentum and impulse is most likely question 4 of paper 1. The following definitions are important. We know that momentum is P is equals to mv, which is the product of mass and velocity of an object. So momentum essentially is the amount of movement which depends on how fast the object is moving and what is its mass. Right? Okay, and then we've got the Newton's second law in terms of linear momentum, which says the net force acting on an object is equal to the rate of change of momentum. Okay, please be aware that F net delta T is impulse. This is impulse. Okay, impulse is the product of net force and time, which is equal to the object's change in momentum. So in other words, if a net force acts on an object for a period of time, it will cause the object's momentum to change. So if we are able to determine by how much did the momentum change in which direction, we're able to have a sense of the impulse on that object. So this happens in the context of explosions as well as collisions, right? And remember, each time there's a collision or an explosion, there's interaction between two bodies. Okay? Body A exerts a force on body B simultaneously or at the same time. Body B exerts a force on body A. That's where we said F by A on B is equals to F by B on A in the opposite direction. Okay, so and then we talk of a isolated system where the total net forces acting on the object is equals to 0. Okay, and then the principle says the total linear momentum of an isolated system remains constant. Okay, so in other words, P initial total is equals to P final total, right? And then we also looked at elasticity of collisions, where you have to compare the total kinetic energy before and after the explosion, right? So these are the concepts around linear momentum and impulse. And we also have the impulse momentum theorem, which is exactly that, as it comes from Newton's second law, right? Okay, now remember, change in momentum is a vector, delta P, right? And we've spoken about Newton's second law, F net is equals to ma. If a net force acts on an object, the object will accelerate in the direction of the net force, right? Okay, and what causes an object's momentum to change is the very same net force, right? And then we've spoken about Newton's third law, force by A on B is equals to force by B on A in the opposite direction, right? And then we also spoke about the impulse momentum theorem and the Newton's second law in terms of linear momentum, where we say the net force during a collision is equals to the rate of change of momentum. So for the same change of momentum in a longer period, the net force will be lesser. Has to do with the application of the Newton's second law in safety, in automobiles or in motor vehicles, right? Okay, and I think we've also highlighted that. So for any long or structured question, it's important that you read the question and understand before you answer the questions. Okay, underline the keywords, very, very important. Remember, velocity, momentum, change in momentum, average force are all vectors. So the issue of direction is very important, because otherwise, when we talk about forces, because when we talk mechanics, we're saying forces are important because of the effects that a force has on an object. It changes the object's state of motion. So be it in the context of collisions or explosions, so we are fine with that. Okay? Always take direction into account. If right is positive, left will be negative. So the minus has nothing to do with size. It's an indication of direction. Okay? And then pay attention to marker location, especially on questions that says calculate the impulse on object A, calculate the momentum. Your final answer must have the correct magnitude and the direction, unless it says calculate the magnitude of a vector. That vector could be change in momentum, could be impulse, could be the average force, it could be momentum. Okay, and then the elasticity of collisions. Remember, you calculate the total EK initial and compare it to the total EK final. You don't equate these two. If you equate, you're immediately assuming that the total kinetic energy before is equal to the total kinetic energy after. And then why do we have to verify that? Because we've already assumed that it's an elastic collision. So you calculate the total EK one side, total EK final on the other side, and then compare the magnitudes. If these two are equal, then we can therefore conclude that it's indeed an elastic collision. If not, therefore it is an inelastic collision. Right. And then the concept of work, energy, and power. It's one of the most poorly answered questions, which, in my opinion, I think learners can still do better on that. Because it's either you understand the concept and its fundamentals, and you don't need to complicate things. Understand the basics. That's what is important. So I've listed a few aspects of work, energy, and power that I think are core to this question. It will be typically maybe your question 5 in section B, right? It says the following definitions and concepts are important. Work done by a force, not just a force, a constant force. So what does work on an object is a constant force? What do we mean when we say a constant force? Let's say we've got a ball that is resting on the ground. Then that ball is kicked on a rough surface, horizontal surface. Okay. Now, the kicking force sets the ball in motion. But between position A, let's say it starts at A and then it ends up at B, which is 5 meters apart. Okay. Now we want to appreciate that the kicking force only exists at A. But between A and B, it's not there. So that kicking force is not a constant force. So even if we draw the free body diagram showing all the forces acting on the ball, we'll have the normal force exerted by the surface, we've got the weight, okay, we've got the kinetic friction which opposes motion. That's it. So the forces that are acting is the normal, Fg and Fk. Now, Fg doesn't do work because we know that W F is equals to F delta X cos theta. Now, theta is the angle between the displacement vector, that's the displacement vector for the ball, and then if you take the normal force is perpendicular. So cos 90 degrees is equals to 0. So this force doesn't do work. This force does 0 work. Why does it do 0 work? It's a constant force acting on the ball, but it does 0 work because it acts perpendicular to the displacement of the object. Then, for the similar reason, Fg is perpendicular. It also does 0 work. 0 work means no work. Okay? And then we've got the kinetic frictional force, which is in the opposite direction. So that's 180 degrees. So if you check here, F kinetic does negative work on the ball. Why does it do negative work? The displacement of the ball is in that direction, right? Kinetic frictional force is in the opposite direction. Angles at a point on a straight line are supplementary. Okay, that's our math. So the kinetic frictional force does work on the ball in the opposite direction. That's what we mean by negative work. Okay, and then we've got the work energy theorem. Work net is equals to delta EK. Right. What does this tell us? The total work done on an object done by a constant net force is equal to the change in kinetic energy of the object. Okay, so the data sheet will give you that. This will help you to record. We've looked at the principle of conservation. Okay, now conservative forces, the exam guide will tell you that Fg is an example of conservative force, while tension, kinetic friction are examples of non-conservative forces. So if you remember all this, okay, then you are able to apply your mind. And so that's our work net, right? Let me just correct that. So the word net means total. So where you see work net, it means total work. Now that's the work energy theorem there. Okay. Now the work energy theorem for me is very, very important. It is directly linked to the Newton's second law. Okay, as we have explained earlier, the total work on an object is done by the total force. Work net is done by F net. So if a net force does work on an object, it is acting on the object. And then the Newton's second law says if a net force acts on an object, the object will accelerate in the direction of the net force. So when the object accelerates, its velocity changes. So the moment the velocity changes, so does its what? Kinetic energy. So the change in kinetic energy of an object is actually a result or a consequence of a net force acting on that object. While the net force acts on the object, it does total work, which will be equal to the change in kinetic energy of that object. So if we identify all the forces doing work and add up the individual work that each of those forces do, we'll get the total work. Either way, if we say change in kinetic energy, which is Ek final less Ek initial, we'll still get the work net. If we calculate the work done by the net force, we'll still get the total work. So this is another very, very important concept in as far as mechanics is concerned, right? And then this one, also very, very important. The examiner likes to use the term using energy principles. There are only 3 energy principles that we know up to thus far. We've got the principle of conservation of mechanical energy. This is only applicable in a closed system or in an isolated system where the total mechanical energy of an object will remain constant at any point, right? And then we've got the work energy theorem, which suggests that the total work done on an object is equals to the change in kinetic energy. And this is directly from Newton's second law, right? And then we've got work done by a non-conservative force. So when the examiner says using energy principles, they are referring to a combination of these or one of these, right? Very important. Here is a practical example. We've got a skateboarder who skates from position A along a track, which is at a vertical height of 15 meters. So this is 15 meters high, right? And comes to rest, which is a vertical, it comes to rest at point D. There is point D, okay? On the other side. AB is frictionless. Okay, we're not going to do these questions, but I just want to highlight something to you. When we say AB is frictionless, we are saying that the mechanical energy of this system remains constant. So in other words, E mech at A is equal to what? E mech at B. In other words, between position A and B, there are only conservative forces acting on the system, meaning that the total mechanical energy will remain constant, which is why between A and B, we are able to apply the principle of conservation of mechanical energy, right? And then they ask you to calculate the kinetic energy of the skateboard B. Now, if they say state the principle of conservation of mechanical energy, the calculation is based on that application. Okay, so it's formula, substitution, answer, which accounts for the 3 marks there. And then again, here's another state. There's another state, and then here is another definition. It's 2 marks. Already, if you answer these 2 definitions and the formula substitution answer, you're already having 7 marks. Now, I firmly believe that it is based on that argument that indeed I think it's easy to understand work, energy, and power, and you can actually get a lot of marks from it, right? Okay. And then in grade 11, this will be most likely your question 7. This is actually based on electrostatics. Okay, grade 11, right? We spoke about the principle of quantization of charge, which is exactly that. Q is equals to NE. It will be presented maybe like this, okay? And then we spoke about the principle of conservation of charge, which says Q nu after separation, and then Q net is divided by 2, right? And then I've also referred earlier to Coulomb's law, the electrostatic force of attraction, Coulomb's constant, Q1, Q2 over R squared. And then here we're talking about electric field. This is around a positive charge, around a negative charge, when positive and negative interact, and when like charges interact with each other. Okay, so this one we know it's something like this. Okay, right? The direction of the field is away. Okay, something like this is what we mean when we talk about electric field. Then for negative charge, also there's a field, a non-uniform field. This is towards, because the unit charge will experience an attractive force. Okay, so these are some of the ideas that you still have to remember from grade 11. So when they say state in words, you don't write the formula. Okay, you state it in words. Okay, the Coulomb's law. Also, pay attention to the mathematical relationship, product of the charges, directly proportional, square of the distance, inversely proportional. And then drawing of the fields is something that you need to remember. And then routine calculations, once again, for 3 marks, is something that you must know. Wherever they say calculate, you must, in these 3 marks, you must know that you have to go to the data sheet, extract or copy the formula as it is given, substitute correctly after doing the necessary conversions if need be, and then the correct answer using a calculator, and include the correct SI unit. Right. What I'm proposing now, because of time constraints, is that usually on the eve of paper, you cannot revise all the 150 marks. So in this 1.5 hour, what we have done, we've reminded ourselves of the topics from grade 10, 11, and maybe first term, things that we did in second term and this term. I think they're still fresh, I assume that. And we can only do so much within the time that is left. And when you are about to write a final exam, you don't spend sleepless nights. That's another thing, because when you wake up Friday morning for the paper one, you need to be well rested so that your brain, can function at its optimal level. You don't want to go there tired and out of sorts. So with that said, I just want to wish you everything of the best. For myself, Temba Nube, we shall be meeting tomorrow again, same time, for our chemistry session. For tomorrow, everything of the best, and goodbye for now.